All right, so this time we're going to have a look at absolute value and what that does with graphs. So first one we'll look at is the absolute value of function x. So this will end up with, well, not symmetry, I suppose it's the wrong way of saying it. It's not symmetric in the x-axis, but we end up getting a reflection. So reflect the bit that's below the axis in the x-axis. Easier to explain with a picture. So here's our random graph. So there's y equals function x. If I want to draw the absolute value of function x, that basically means I can't get any negative numbers as an answer. So anything that is negative will reflect above. And so it'll do that sort of thing to our basic graph. So that's y equals absolute value function x. Whatever's below, reflected above. Now, function absolute value x, what does that mean? Well, that means we're only substituting positive numbers into the function. So the effect of that one would be symmetry in the y-axis, and this one will be symmetric. So whatever is positive gets reflected across. Again, let me explain that with our picture. So there's our random graph, but we're going to substitute in the absolute value of x. So all these negative numbers, negative x's, don't exist, because you can never sub those negative numbers in. But what ends up happening is whatever's on the right gets reflected on the left. Because when you substitute in, say, -1, you're substituting first of all into absolute value of -1, which is +1. So when you sub in -1, you get the same answer as +1. Sub in -2, you get the same answer as +2. And so you get that reflection in the y-axis. Okay, so this time, absolute value of y is equal to function x. This one will have symmetry in the x-axis. So we're going to reflect the bit where the function is positive in the x-axis. Because what we're now saying is we can only get positive answers. There's our graph. The bit below disappears because now we can never get those negative answers. But what's above gets reflected below. So when you sub it in, you might get a function answer that, say, was -2, but we're saying we want the absolute value of that. So instead of getting the answer for -2, it'll get +2 as the answer. So we get reflection in the x-axis. Now, I might have got a bit carried away with this. Now let's have a look at absolute value of y is equal to function absolute value x. And really, when you think about it, it's a combination of the second and the third one. So we could draw the second one and then do the absolute value of y on that. So what will we end up with? We have symmetry in both the x and the y-axis. So we're going to reflect whatever's in the first quadrant. It'll end up going into all 4 quadrants. So there's our graph. Basically, we've only got the first quadrant answer, and it'll get reflected into all 4. So that would be absolute value of y is equal to function absolute value x. What about absolute value of function absolute value x? So this time we'll get a combination of the first and the second one. So I would draw y equals function absolute value x first, and then apply the first one to it. So symmetry in the y-axis, reflection in the x-axis. So there's our random function. There's function absolute value x. That's the one we drew before. But we're now saying the absolute value of that. So whatever is below gets reflected above. So that would be absolute value of function absolute value of x. And you have great fun playing with absolute value. What about absolute value of y is equal to absolute value function x? What's going to happen with that one? This one would be a combination of the first one and the third one. So symmetry in the x-axis and then reflection in the x-axis. This is wonderful. Have a look at this. So there's function x. That would be absolute value function x. Whatever's below is reflected above. But then what did we do for absolute value y? Whatever's above gets reflected below. So we end up with that wonderful. All right, so that's absolute value. So I might have got a bit crazy with how far I went with those. But that's the sorts of different graphs we could draw with absolute value. Let's have a look at square root. Okay, things to notice about square root graphs. First of all, we know we can only find the square root of a positive number. So whatever's negative on the original graph just goes away. It's no longer in the domain. And we also know the square root is always going to be positive. So here's random graph. Straight away, whatever's below goes away. Can't find the square root of those, so they're no longer in the domain. Now, when it comes to stationary points, they will still be stationary points, but the y values obviously will change, unless the y value is 1, of course. Square root of 1 is 1. So here's our original graph. Our turning point up here, well, it's bigger than 1. Find the square root of a number bigger than 1, it will go smaller, so it'll come down a bit. Horizontal and oblique asymptotes, well, we'll find the square root of those things, and well, the vertical asymptote will remain, because if it wasn't in the domain of the original one, can't be in the domain of the new one. And that horizontal one, well, its value is less than 1. Find the square root of a number less than 1, it's going to get bigger. So it comes up a bit. You may recall with that square one where we said where the old one was below, the new one's above, and vice versa. Same sort of thing happens with square roots, but it's the other way around. So this time, if the square root, sorry, not if the square root, if the function's bigger than 1, then the new curve will be below the old curve. But if its function's less than 1, then the new curve will go above. So 1 becomes an important point because the square root of 1 is 1. So we'll plot all those in. So what did we say? If it was below 1, then the new curve will be above. Find the square root of a number less than 1, it's going to get bigger. So we're going to go above, we'll go through 1, and then we'll go below. Now, our X-Intercepts, got to look at those very closely. And here's why. Have a look at this. I don't know if you've ever seen this before, but if you've got x to the power of a on b, what do these graphs look like? And I'm using the thirds for an example here. So there's x to the power of 1/3, there's x to the power of 2/3. Basically, if that fraction is below 1, and I'm just looking at the first quadrant, the curve will be concave down. So you'll notice both x to the power of 1/3 and x to the power of 2/3, it's concave down. Now at 0, we have a vertical tangent, if I was to draw a tangent in. If the top number's odd, I will get rotational symmetry like an odd function. If the top number's even, then you'll notice I have the reflectional symmetry there. And obviously 3 on 3, well that's just 1. So it goes from concave down, it hits 1, I've got a straight line, but when I go greater than 1, now it goes to concave up. So 4/3 would be concave up, 5/3 concave up, 6/3 would be concave up, and again depending on whether it's odd or even with the different symmetries there. But notice now at the origin, we no longer have a vertical tangent, we have a horizontal tangent on each of those. Now why is that important? Well, because we're about to draw a square root graph. A square root is, of course, the power of a half. Here's a bit of a summary of what might happen. Think about what would happen if you square root the graph. Now, if you know the equation of the graph, fantastic. Because obviously, if I find the square root of x to the power of 4, I'm going to get x to the power of 2. And so the square root would be the parabola. X cubed, if I find the square root of that, can't find the square root of a negative number though, so the bit below disappears, and I get the shape. Well, what is it? 3 on 2. 3 on 2 is bigger than 1, so it's concave up. X squared, well, find the square root of x squared, it's x to the power of 1. So it's coming in like a straight line. So it sort of looks like an absolute value one there. 5/3. Okay, there's what 5/3 looks like. Find the square root of that, you would get 5/6. 5/6 is less than 1. So it goes to concave down, and we get a vertical tangent. And the last one there, 4/3, square root of that would be 2/3, which is less than 1. So we get a concave down one with a vertical tangent. Now our one, I don't have an equation for. So I've just kind of got to guess. Now, each one of these were coming through like a straight line. So I'm thinking the root's going to be to the power of 1, whatever the root is. If I found the square root of that, it would become 1/2. 1/2 is less than 1, so I'm expecting a concave down and a vertical tangent. So 0 still exists. Well, it's a little bit... I might have exaggerated the end one slightly to show it's a vertical tangent. Bit of an exaggeration. But we've got the concave down bit, vertical tangent. Each of these... Oh, gee, it's really dodgy, isn't it? But each of these is concave down. And remember, I'm trying to go above the curve, below the curve, above the curve. But that's the idea I'm trying to achieve there. There's y equals the square root of function x. What's a really interesting question is, instead of asking y equals the square root of function x, asking y squared equals function x. And what happens there, you now reflect, because now you get both plus or minus the square root. And so you get a lovely reflection in the x-axis. There we go. So 5e, we'll have a bit of a play with absolute values and square roots.